our speaker today, Professor Greeshma Gadikota, hopefully I pronounced correctly, from Civil and Environmental Engineering. So I look at her resume, I print out, right? So already very impressive. She got her bachelor degree in chemical engineering, so we're in Oakland, right? So in the right place from Michigan State, and you got two master degrees. We got typically have two bachelors, but you got two masters, right? In both chemical engineering and operational research from Columbia, and you got also your PhD degree there. So Dr. Gadikota received the Department of Energy Career Award. I know that's very competitive. Also, take a more generous than NSF. And when I look at her resume, she directs the energy and resource recovery group. I look at that's very close to what I'm doing. And then, very embarrassing to introduce a colleague. This is my first time I ever met her. It's very embarrassing. But then, when did you arrive here? We said 4 weeks ago. Actually, that made me feel better. She really knew to Cornell, but you were at Wisconsin at medicine and moved here. So I think that's all of you all. I'm eager to learn what can I say. Right?
Thank you, Max. Thank you, everyone, for being here this afternoon. It's really my pleasure to be here, and thank you for the invitation and the introduction. So I have, without further ado, I just wanted to talk to you a little bit about energy and resources today and what we as chemical engineers can really do to address some of the emerging challenges in the area of energy and resources. So I don't really want to scare you with this long-winded title. But my intent really here is to tell you a little bit about some of the interesting chemistries that happen when you have fluids interacting with some really interesting solid interfaces in extreme subsurface environments and also in engineered processes. So with that said, a little bit of framing is needed, right? So we live in a society where we consume a lot of energy, where we consume a lot of resources. A lot of these resources come from subsurface environments. So one of the questions that we actively ask in our group are, what are some of the subsurface processes that need to be investigated when we think about the enormous quantities of fluids that we recover or the fluids that we want to store? And not just fluids, but there's also a lot of spent nuclear fuel, right? So there are a lot of these residues that are left over from energy recovery processes. And what do we do with them? How do we harness the vast space that we have underneath the ground that we walk on, and what is it that we can do in order to utilize those spaces? And not only that, but once we recover these fluids and materials, if you like, and we put them through a lot of very interesting conversion processes that we've spent the last 100 years utilizing our intellect and talents to develop, one of the major questions that we now have to grapple with is, how do we actually integrate the treatment of greenhouse gases, toxic gases, and effluents with engineered and natural materials, right? And one way to think about this is in the context of the carbon cycle, right? So we spent a lot of time thinking about how we can extract carbonaceous resources from subsurface environments, put them through a lot of really interesting energy and resource conversion pathways. But now we actually have to deal with all the CO2 emissions that are being put out into the atmosphere. So what do we do with that? So hopefully my talk this afternoon will give you a few insight into how we are applying fundamental science in order to address some of these challenges. So with that said, there is a very rapidly changing landscape of energy and environment. So 10 years ago, when I started my PhD, or was thinking about starting my PhD, the world was talking about coal, right? We're talking about how coal cannot be phased out and how we need to manage coal by putting in carbon capture and storage technologies. And very quickly, all of that conversation changed because natural gas came into the picture. And what natural gas did was it effectively made the United States from being an energy importing economy to an energy exporting economy. That has significant geopolitical implications. But what does it really mean for the world around us, for the environment around us? Well, what that did was that basically now, as a result of being able to harness a lot of these subsurface resources, more than 80% of the energy that we use is actually derived from the subsurface environments. Fossil fuel consumption contributes to more than 75% of global CO2 emissions. And interestingly, more than 50 billion, that's billion with a B, cubic meters of fresh water is actually consumed annually for energy production. And what is interesting is that with these changing fuel mixes, we have differences in carbon densities, and we also have impacts on global water withdrawals. So now the question is, so we're a bunch of engineers, we put our engineering hats on, and then we think, what is it that we can do about these challenges, right? And even before we think about what we can do, we need to frame the questions that we want to address. So the societal challenge that we want to tackle here is, how do we meet a growing demand for energy and resources while reducing detrimental environmental impacts? The technological challenge that we want to address is, how do we develop these integrated processes so we can meet the energy demands that we have with inbuilt environmental controls? So how can we develop neat little devices, if you like, where we can do a lot of interesting conversions so we can produce the energy and resources that we need while putting away the stuff that we don't need? Can we do that? And the scientific challenge is that in order to even take the technological route, we need to develop a very fundamental understanding of some of the complex chemical, physical, morphological, and mechanical interactions that arise as a result of trying to make this happen, right? So in my talk, we'll touch upon a few of those important aspects. And what is interesting is that when we think about framing these challenges and thinking about the approaches that we want to take, we really need to take a cross-scale approach, because there's so much that we don't understand about fluid organization and transport properties at the molecular scale. There's so much that we don't understand about fluid-driven structural and morphological changes in materials and how these two impact material and energy conversions at scale. So there's a lot of fundamental science that needs to be done at the smaller scale so we can actually start to have some impact at the larger scales. So in order to do that, in our group, we use molecular scale models. We combine that with in-situ material characterization techniques. We are in the process of developing multiphase reaction environments, if you like, where we can do some of these interesting energy conversions with inbuilt environmental controls. And we want to eventually translate some of that fundamental understanding into something that is real and actionable in the real world. So hopefully we'll get there over the course of the next few years. So with that context, so as engineers, right, we spend a lot of time problem solving. We spend a lot of time drawing boundaries around a given process. We like to think about what is going in. We like to think about what is coming out. So one example is where we can take acid gases. We can react that with alkaline materials, and we can produce mineralized solids. We can take multi-gas streams. We can put them through some kind of a separation process, and we can get some post-adsorption lean gas. We can take wastewater. We can develop novel functionalized materials, and we can produce clean water. We can do a material balance, energy balance. We can tune these chemistries, no problem. We have the toolkit. But the challenge is when you actually start to think about things that you cannot see, things that are happening in the subsurface, but it's not easy to draw a boundary around. So what do? So just to give you an example of some of these emerging challenges. So one of the important aspects in being able to put away CO2 emissions at the gigaton scale is to be able to harness the subsurface environment. So geologists and hydrogeologists particularly have been doing a lot of work in taking CO2, putting it in the subsurface environments. There are a lot of uncertainties about the mobility of the CO2 once you put it in the subsurface. Is it going to mineralize into a solid? Is it going to stay mobile? And why does it really matter? Because the folks who are taking the permits on being able to do some of this, they need to be able to show what the fate of the fluid is going to be, right? Is it going to stay underground over the course of the next 10 years, 100 years? How do we project that forward? A lot of engineering, a lot of fundamental science to be done there at those extreme conditions, which you actually cannot see, but you still need to mimic. There's a lot of interest. I'm sure a lot of you have heard, not necessarily in New York State, but other parts of the United States, where high-pressured water is being fed into the subsurface environments, induce fractures to get methane out. Challenge there is that now there are a lot of methane leaks. As a result of those methane leaks, we see fugitive emissions happening. A lot of interest in being able to store nuclear waste in the subsurface environment. Problem is that corrosion of nuclear waste, again, produces gases like hydrogen, and once hydrogen migrates to the above ground, you can actually get explosions. Also, there's a need to track these fluids in the subsurface environment. So there's a need to develop tracers there as well. So being able to apply some of the chemical engineering thinking to address some of these challenges is really, the way forward. And the question then is, we zoom out of this challenge a little bit, and then we take a look at what is it that we need to do in order to balance high-risk energy recovery activities that are already going on with environmental sustainability. So what is it that we can do, right? So we go back, I have my pencil, my paper, maybe a laptop, maybe access to a few models. So we can start thinking about, okay, I really want to understand how these fluids behave at the molecular scale in these subsurface environments. So I'm going to talk to you this afternoon about 3 aspects. The first is I'm going to talk to you a little bit about some of the insights that we're able to get about fluid organization and transport properties in subsurface environments using molecular scale models. I'm going to talk to you a little bit about structural and morphological features as a result of fluid-induced changes in representative subsurface environments. I'm going to talk to you about some of the material and energy conversion pathways that we are also exploring. So with that said, we'll talk, the first part of my talk is about predicting fluid organization and transport behavior. Next we'll talk a little bit about multifunctional fluids, cross-scale characterization approaches, and geologically inspired processes, right? So what is it that nature is doing that we can mimic and make it go faster, right? When it comes to developing sustainable energy and environmental pathways and processes, if you like. So I'm going to start off by talking about the first part of my talk. And here we are harnessing molecular dynamic simulations as a tool to understand the role of solid interfaces in confinement on fluid organization and transport. And the motivation for this really emerges from the interest in being able to store CO2 in depleted oil and gas reservoirs. But nobody's really done a lot of work about understanding the fate of these fluids in these environments. So the question is really simple. If I have to put CO2 in a reservoir that still has some methane, that still has some heavy oil in it, what might that do to the pore space, right? Is it going to close up the pore space? Is it going to open up the pore space? We don't know. But can we predict it? So with that, there are 3 questions that we'd like to address. The first is, how does hydration influence the organization of transport properties of confined gases? So the question here is that if I have a pore space and most pores in the subsurface environments are filled with water, and if we try to inject CO2, what is that going to do to the way these fluids are organized in these confined environments? The second question that we'd like to address is, what is the influence of pore size on CO2-induced displacement and diffusive transport of some of these geofluids? And how does nano-confinement and CO2 influence the aggregation of polyaromatic macromolecules? So this is kind of interesting because, I'm not a petroleum chemist. I'm not trained as a petroleum chemist. I do a lot of work in CO2. But what is interesting is that in the process of oil and gas extraction, they extract a lot of light oils, but often leave the heavy stuff behind. Now, what is the heavy stuff chemically? It's just a whole bunch of really, really large macromolecules that are known as asphaltenes. A lot of work has been done in asphaltenes. Basically, no work has been done on looking at CO2 interactions with asphaltenes. So this is our attempt to kind of probe that understanding using some of these molecular scale models. So my student, Sohaib Mohammed, and I did some of this work. This was published over the course of the last year to year and a half. So I'm going to give you some new insights into this. And the power of molecular scale simulations in this context is that it actually allows you to simulate some interesting scenarios that you can't necessarily mimic, right, in an experimental setting. So you can put in different types of conditions. And yes, it may not be completely representative of a true experiment. At least it gives you that insight into what may be going on. So you can then go and design a very targeted experiment. So with that said, I'm going to start talking to you a little bit about molecular dynamic simulations at calcite water-gas interactions. The reason we're interested in calcium carbonate is because it's one of the primary constituents of limestone, and it actually forms most of the world's hydrocarbon reservoirs. This is particularly true in places like Qatar, and there's a lot of interest in being able to put away the CO2 in some of these environments. The question that we want to ask ourselves is that if we have no water in confined porous environments versus water to the order of 1 gram per cc in these environments, how is that going to influence the organization and the transport? So here we have nanopores in these materials, and here is a descriptor of the way we went about setting up our molecular scale simulations. I'm happy to forward along the paper for those of you who are interested. But basically what we found is that when we have no water in these porous environments, both CO2 and methane have a strong tendency to be absorbed at the surfaces of these interfaces, right? So let's just say this is my pore space, this is my concentration profile, if you like, or my density profile. Both CO2 and methane prefer to be absorbed at these surfaces. On the other hand, if I have a water that with the density of that of bulk water in confinement, what happens is that now my CO2 and methane prefer to be solvated at the center of this pore. Now my water forms this layered water structure in confinement, so there's some solvation effects that are happening. So, and these are two intermediate states of water. This is when we have a single layer of water, when you have slightly more water molecules. And again, as we continue adding more and more water molecules into these confined environments, we start to see enhanced solvation effects. So this is interesting because up until now, when folks use conventional models to predict what fluid solubility is like or how gases might dissolve, they've always neglected the effect of the solid interface. But it turns out the solid interface actually has a very important role to play in some of these conditions. We also draw up some concentration profiles. So this is the case where we have no water. This is the case where we have a lot of water. This is basically my solid interface. So you see this contrasted line right there. And what is interesting is that as the concentration of water increases, so this is no water to the most amount of water, we basically see a high concentration of gases in the center of the pore. What is also interesting is that we see CO2 at the center of the pore, but it looks like the methane wants to exsolve, right? And it wants to actually form different phases. At least that's what this figure tends to tell us. So we haven't really gone into probing the thermophysical properties of methane in confined water with CO2 present, but at least this is a first indicator that some of that interesting phenomena might actually be happening. So now we'll move on to the second part of my talk, where we'll look at the effect of pore sizes. So here we look at pore sizes that vary all the way from 2 nanometers to 10 nanometers. So really tiny, basically pores to the order of single digits. And we want to understand how, if we were to try and store CO2 in a subsurface environment where some oils may be present, how would the CO2 organize itself, and why would it organize itself a certain way? So these are basically silica nanopores, and we fill these pores with CO2 molecules, toluene and propane. So we just chose propane and toluene as example, just as a case study, if you like. And what we find is that, when we have CO2 and when we have propane and toluene, of all these molecules, CO2 has the strongest affinity for the solid interface. So basically, if you have a mixture of these components, CO2 prefers to preferentially adsorb onto the surfaces as opposed to these hydrocarbon molecules. We can take this, we can calculate a selectivity if you like, right? And a selectivity is basically the adsorbed number of CO2 molecules with respect to the hydrocarbon molecules. This gives us an insight into whether the CO2 is going to maybe pull some of these molecules away from the solid surfaces, or whether it's going to displace them. If it's going to displace them, how is it going to displace them? Is it a function of the pore diameter? Can we get some of those insights? So it turns out that CO2 with respect to propane, CO2 has a strong tendency to displace propane, less so in the case of toluene. So the larger and the heavier hydrocarbon molecules have an affinity to stay close to the surfaces. Next, we look at the diffusion coefficients in confinement. And what is interesting is that both CO2 and propane have similar molecular weights. So if you just have CO2 and propane, just these two fluids, then they tend to have similar diffusivities. At least that's what these two lines show. So my black is CO2, my blue is propane. But on the other hand, if I just add toluene, what is interesting is that now my propane has a higher diffusivity, and the diffusivity of CO2 slows down. So just by having multiple components in confinement, we are changing the transport behaviors of these nanoconfined fluids. At least this is, some of the first evidence of that. And when we have toluene, when we have CO2, toluene is a much heavier molecule, has a tendency to get transported much more slowly. CO2, again, in comparison, has a higher diffusivity. What is also interesting is that the diffusivity is not just one value, right? So if you're closer to the surfaces, there's basically very slow transport, but if you're in the center of the pore, transport is much higher, right? So there's this anisotropy in the way fluids are transported in confinement. And those were some of the insights that we were able to glean. Now, in this third question of what is the influence of solid interfaces on the way some of these polyaromatic hydrocarbon molecules organize themselves in the presence of CO2, we did simulations with molecules that are known as asphaltenes. So typically, in the oil and gas business, what people have done is they spend a lot of time thinking about how they can get the alkanes out or the cycloalkanes out. They like all of these molecules except this one. The reason they don't like this one is because it basically causes a lot of pore fouling, and it is one of the major reasons why recoveries are not very high and why gas fields tend to get, or oil and gas fields tend to get shut down. Our interest is that if we were to stick CO2 into some of those reservoirs, what kind of behaviors might we expect to see? So these molecules have been quite tricky. So there's been a lot of work in resolving their structures. A lot of NMR work has been done, AFM work has been done. So we can actually take some of the structures and now we can start simulating them, right, to understand how these molecules might actually behave in the presence of solid interfaces. Again, a lot of work has been done in just looking at how these molecules just stack up or just organize themselves, but the effect of the solid interface has been long neglected. So we looked at the influence of silica surfaces and calcite surfaces and how these asphaltene molecules might organize themselves. And we took these two structures from literature. And what we found was that when we have these solid surfaces, right, and then we plot these profiles of these asphaltene molecules as a function of location, we find that these asphaltene molecules have a strong tendency to agglomerate at these edges, right? And that is true in the case of both the silica surface and in the case of the calcite surface as well. If you just have a bulk unconfined fluid, then we can expect to see the clustering of these molecules to occur. So by the time we reach about 40 nanoseconds, all of these molecules have basically self-organized themselves. They've basically organized themselves into like a compact colloid-like structure, if you like. But then once you have these pores, there's competition, right, between trying to self-organize versus absorbing onto the pores. So we start to see smaller clusters as a result of that. We also find that when we have no CO2 versus a lot of CO2, CO2 actually accelerates the rate at which these molecules kind of self-organize themselves in confinement. So this was an interesting finding. Now, so what this is telling us is that if we actually put CO2 into the subsurface environments, just based on some of these models, we might actually cause these asphaltene molecules to aggregate faster, and that may actually not be a good thing. So now we actually have to engineer materials that can go into the subsurface that can break down these asphaltene molecules in the presence of CO2. So there is some engineering that needs to be done there now that we actually know how CO2 starts to behave in these environments. So this is, again, just an example of how the fluid is organizing itself in confinement. So if we have a CO2 mole fraction of 0, then basically your toluene has a layered structure. This is the solvent in which the asphaltene molecules are suspended. But then as we start to have more and more CO2, then we tend to form miscible phases, and the asphaltene aggregation tends to occur in the center of the pore. So depending on the amount of CO2 that we have, we can expect to see some really interesting behaviors there. And also when we look at the asphaltene aggregation behavior, you can start to see pi-pi interactions that leads to this core-to-core stacking, or you can get these T-shaped interactions as well, as you see here. All of this starts to become important and interesting if you're trying to engineer some kind of interesting subsurface fluid or material to break up some of these aggregates. So from this first part of my talk, I just wanted to give you a few examples of the power of molecular scale simulations and being able to surface environments. There is still so much work that needs to be done in refining the force fields and being able to come up with robust models, if you like, that are actually representative of some of these subsurface environments. But effectively, this is kind of a first foray, if you like, into predicting some of these behaviors. So the key takeaway from this is that multi-component fluid interactions with solid interfaces really influence the organization, transport, and absorption behaviors of fluids in confinement. Experiments are hard to do, so we need to develop bounds in the experiments that we want to design around this. So being able to use molecular scale simulations actually helps guide us where we want to target our experimental efforts. So now I'm going to move into the second part of my talk, and in this talk we'll talk a little bit about some of the cross-scale characterization approaches and our very initial forays into thinking about designing some subsurface fluids, if you like. So with that said, I have some colleagues at the Pacific Northwest National Laboratory, and they came up with this really interesting, they discovered that when you have CO2 interacting with a very interesting molecule, which is known as polyalylamine, it actually causes this molecule to swell a lot. And when this molecule swells in the presence of CO2, it can actually induce fractures in rocks. Now, what does this really mean? This means that if we have a geothermal reservoir with really, really tight pore networks, we can actually use these materials, pump CO2, have enough mechanical pressure to actually fracture these rocks. And the process of fracturing these rocks, we can inject more fluids and also recover more fluids. And the process of doing that, we can also recover more heat. So this was a very intriguing idea, the fact that you can actually do something in the laboratory to have an impact in the subsurface environment. So we started exploring this concept a little bit more. Challenge is that a lot of these fluids were basically developed for high temperature and high pressure environments. But a lot of heat that we want to recover, for example, tends to be from more shallow reservoirs, right, where temperatures and pressures are not necessarily that high. So what is it that we can do to construct CO2 responsive phase-changing fluids for a wide range of temperatures and pressures? So that's where we actually took some inspiration from Professor Archer's work in developing nano-organic hybrid materials. So here we have a silicon nanoparticle. We can put in some ionic bonds, some covalent bonds, and this is some, a lot of extensive work has been done in this area in engineering these materials. And my student Hussein Asghar was interested in thinking about, is there a way that not necessarily harnessing the chemistry, but harnessing the concept to actually do something with these molecules? So what we did was we have a silicon nanoparticle, and we did not extensively functionalize it, but basically when we have this in the presence of polyalylamines, these polyalylamine molecules tend to organize themselves using hydrogen bonds. And what happens is that in the presence of this SiO2 particles with PAA, you actually have enhanced gel formation. So the way these molecules cause fractures is through hydrogel formation. So in the presence of CO2, they form hydrogels. If you have higher pressures, higher temperatures, more extensive formation of hydrogels, they go in, induce higher mechanical strength, cause rocks to fracture, if you like. What is also interesting is that when we have these SiO2 molecules, SiO2 with PAA bound, we actually get higher CO2 uptakes as well. And this is not only because of the CO2 binding to the functional groups, but the CO2 actually getting trapped in some of those interstitial spaces also. So there's an entropic effect on top of the enthalpic effect. And we can also regenerate these hydrogels. So if you just put these hydrogels, if you just pump a lot of water, they tend to get hydrolyzed, and they tend to get regenerated as well. So in some, you could call it effectively a reversible fluid, if you like. We also wanted to understand what is happening to these materials, so we started harnessing ultra-small and small angle X-ray scattering measurements. And for those of you some of you who are familiar with scattering, some of you who are not, basically the principle is that when you scatter when you try and scatter materials that have very ordered crystal structures, if you like, that is using wide-angle X-ray scattering, you get a crystal signature of these materials, right? That's basically X-ray diffraction or wide-angle X-ray scattering. If you scatter from slightly larger length scales, then you start to get some insights into the nanoscale morphology of these materials. If you scatter from some of the larger length scales, now you're approaching some of the micrometer-sized features that you can extract. Challenge is that you could scatter from a slice of cheese, you could scatter from a slice of wood, your scattering curve could actually look the same. So you need to have some a priori insight into what the morphology of this material actually looks like, even before you can go in and start extracting some of these microstructural features of these materials. So we started doing some X-ray scattering on these effectively disordered materials, if you like. Basically, they're a bunch of polymers, right, organizing themselves around silicon nanoparticles in the presence of CO2. And what we find is that these are the small angle and ultra small angle X-ray scattering curves. So these undulations that you see here, these are a result of scattering from the silicon nanoparticles. And here are some of the features that we see. We attribute that to scattering as a result of the hydrogel formation. So we can extract things like power law slopes and effective dimensions of these materials, and we basically find some of these hydrogels forming. So in the interest of time, I'm going to move forward and give you just a few more examples. So that was just one example of some of the materials that we're probing to perturb the subsurface environment, if you like. The next step of studies that we want to investigate involve actually understanding some of the mechanical behaviors of these materials, like I described earlier. So now the next question is that coming back to the problem of CO2 storage, right? Can we actually store CO2 in some of these nanoporous environments? So it turns out that there's a lot of interest in being able to harness nanopores in the subsurface environments, particularly materials that are rich in clays. So for those of you who have or have not worked in the world of clays, they're basically aluminosilicate structures, and they tend to be intercalated with some metal ions, similar to, say, battery materials, right, where you're trying to intercalate lithium ions and in some of those spaces. Now we want to understand is if we actually pump CO2 into some of these materials, are these materials going to shrink? Are they going to swell? If they're going to shrink, then is that somehow going to influence the pressures in these subsurface environments, and how do we probe that? So that's where some of these scattering techniques can be really useful. So you can think of a clay as a series of aluminosilicate nanosheets, and in between these nanosheets, you basically have a layer of water, right? So if you pump CO2 through, and if your CO2 is intercalating or dissolving, then you would expect, perhaps, that this clay would swell. But on the other hand, if you're dehydrating it, then you would expect this to shrink. What we find is that as we go up in temperature and as we go up in pressure, so for example, if you're at 90 degrees centigrade at 80 atmospheres, this two-layer peak that we have here that corresponds to the scattering from this one nanosheet and this interlayer basal spacing, right? That is the basal distance right here. If we have two peaks, one is indicative of a one-layer hydrate, the other one is indicative of the second-layer hydrate. So this is two mixed states of one and two-layer hydrates. As we add more CO2, we're depleting the second-layer hydrate. We have one layer. As we add more and more CO2, we're depleting this more and more to the point where there's no water left. And not only that, we're basically shrinking these materials down. So these materials that actually started out with a representative basal distance of 15 angstroms now are at about 10 angstroms. So effectively, we are shrinking them down by about 5 to 6 angstroms, if you like. And these are some of the first set of data, and this actually goes counter to some of the work that was reported at PNNL, where they actually showed that when you have CO2, it goes into some of these environments and causes the materials to swell. We actually see shrinkage as a result of CO2 interactions. So that was an important finding for us. So another example of fluid-solid interactions is looking at what CO2 might actually do when it comes to fracturing materials or fracturing rocks, because there's a lot of interest in not just using water, but in using CO2 to perturb the subsurface environments. And this is also true when it comes to using CO2 to perturb geothermal environments in the subsurface environments. So I'm not a geologist, I'm not trained as one, that's a disclaimer. But with that said, we started getting interested in some of the chemistries of these materials. So these materials are a mixture of carbonates, clays, quartz, and feldspar. And they have varying levels of clays, carbonates, and a mixture of carbonate and clay-rich rocks. Turns out that when you react these materials with just dry CO2, not a lot happens. But then when you react these materials, I'll just go back one, when you react these materials with a mixture of CO2 and water, a lot of changes happen to the structures and the microstructures of these materials. So to non-invasively probe what is happening to the pore structures of these materials, we did some ultra-small and small-angle X-ray scattering measurements. So as an alternative to BET measurements, where you're using gas absorption to probe some of the changes in the pore structures of these materials, we're actually using non-invasive X-ray scattering methods. So from this, we can see that, so my black is my unreacted shale. With just dry CO2, not a lot is changing to the pore structures. when we have CO2 and water mixed together, we see significant increases in the pore volumes of these materials. So clearly, having a mixture of CO2 and water is changing the pore structures of these materials. Turns out what we're doing is that we're dissolving a lot of the carbonates that are present in these materials. And these are some microtomography images. I'm not sure if you can see them very clearly, but I can tell you what we're seeing. Effectively, we're starting to see some directional type fractures in these materials as a result of exposing these materials to supercritical CO2 and water. Now, another example is that of what is actually happening to these materials when we start to heat them. And can we actually determine the microstructure and structural features? So a lot of work has been done in understanding, for example, how you could recover fluid, right? A lot of work in the oil and gas industry, or even with geothermal, understanding how you can circulate that fluid. But what is actually happening to your material when you are subjecting these environments to this thermal cycling, if you like? So we used ultra small angle, wide angle X-ray scattering measurements, looked at what is happening to shale as an example, found out, again, this is basically heterogeneous material, has a mixture of a lot of different materials. But what is interesting is that when we go up to high temperatures, it starts to behave like a sintered solid, right? So for those of you who work in the area of ceramics, what we find is that this layered clay that is present starts to lose its layering. Calcium carbonate that's present loses its CO2. Quartz changes its structure. And we end up forming these very, very high dense silicate structures instead. And these silicate structures tend to have, they tend to basically fuse, and you get much larger particles, and you also squeeze out the little porosity that's present, right? And turns out that when you heat it to 650, you open up the pore spaces because you are basically decomposing the CO2 or removing any water that may be present. But then when you are heating it up to temperatures greater than 700, you're squeezing out the pore spaces, basically causing sintering to happen in the subsurface environments. So some of the engineering phenomena that you actually see in the lab is something that actually happens in the subsurface environments as well. Also looked at small angle scattering curves. Not a lot to report between the 25 to 650 range. A lot of interesting changes happening above that. Basically, what happens is as you start to heat, and you start to get some ordered crystals forming, you start to see some smoothing of these interfaces. At least that's what we infer from our scattering curves. So the second part of my talk is just intended to give you an example of how some of these emerging characterization techniques are really useful in basically probing phenomena that you can't necessarily see with your eye in the subsurfaces, but instead you can mimic in laboratory scale environments. So, the good news is that I'm at the third part of my talk. And for some of you who are really interested in reaction engineering and multiphase environments, this may actually be of a lot of appeal to you. Because what we're proposing to do here is that we're actually proposing to take a lot of calcium and magnesium bearing materials and using a thermodynamically downhill route, convert them into calcium and magnesium carbonates. So a lot of you have heard about carbon utilization, perhaps taking CO2 and upcycling it into a hydrocarbon bearing molecule. In this case, we're actually taking CO2 and taking it thermodynamically downhill route, converting it into a carbonate. Question then becomes, do we have enough materials that we can do this with? Turns out that in order to balance the acidity of the CO2 molecule, you need a lot of alkaline materials. So we actually do have a lot of materials in, for example, here on the western coast of the United States. We have the basalts. We have some magnesium silicates here in the northeast. A very good example is that in Oman, where there is basically direct air capture of CO2 occurring in natural environments using magnesium silicate materials. Question then is, can we mimic some of this both in the field setting and in an engineered setting? Can we draw inspiration from these to do something new and interesting? Turns out that if we actually inject CO2 into some of these reservoirs, we could actually completely carbonate some of these reservoirs over a timescale of about 1 to 2 years. This is something that folks have actually observed in places like Iceland, where they're doing CO2 injection projects. Chances are that, it's great for storing CO2, but we still don't know what that's going to do in terms of fracture propagation in these materials. And what you don't want is to actually have fluids bearing salt getting trapped in some of these pore spaces, the water being evaporated, saw crystallization occurring and these materials to disintegrate and to fall apart. So with that, we started looking at some of the representative materials where we could start mimicking carbon mineralization, if you like, basically taking CO2, converting into a carbonate. And some of the most reactive materials are magnesium silicates and calcium silicates. There are some other materials which are aluminosilicates that are widely available and abundant, but very less reactive. What this tells us is that we could just put CO2 into these reservoirs and let the earth act as a reaction system, naturally convert them into carbonates. We can take these and develop engineered processes to convert them into carbonates instead. So what is it that we're doing in that front? So I did a lot of work basically looking at multiphase reaction environments where you can have CO2 in the supercritical phase, how that interacts with water, and how that might interact with a co-solid that's present. So basically you get CO2 dissolution in water, you get speciation, you can dissolve the mineral at the same time, you can form calcium and magnesium carbonates. But if you look closely at these temperatures at which this is happening, this is all happening at temperatures above 150 degrees centigrade and pressures, CO2 partial pressures of above 139 atmospheres, right? So then this kind of brought about the question of, can we do this more elegantly at room temperatures and room pressures? Is there a way of being able to understand this and do the latter? Also, it turns out that balancing the pH in these environments is really important. We also explored the two-step carbon mineralization approach. Here we basically leach out the calcium and magnesiums and then bubble CO2 through to produce high purity calcium magnesium carbonates. This is of a lot of use for a lot of commercial applications, but again, a lot of consumption of acids and bases. Can we do this in a slightly more elegant manner? So my student, Mission Liu, and I, we came up with this approach, which is known as the aqueous alkaline amine looping approach. It's a mouthful, but here's what we're trying to do. So we want to design the chemistry of our aqueous environments. So we have basically an amine solvent, if you like. And what the amine solvent does is it actually captures the CO2 that may be present in the flue gas, converts that into a carbamate. And then what we want to do is we want this carbamate or bicarbonate to react with the dissolved calcium or magnesium. So we can form the magnesium or calcium carbonate and regenerate the amine in the process. So effectively, we are trying to design a system where you can get a lot of this multiphase reaction chemistry going, so you can start doing this with flue gas streams in a single step. We can do this with, I would say, point sources of CO2, but if we engineer our chemistry just right, we could probably be doing this even with direct air capture of CO2, but that's kind of a long shot. We're working on that. So this is one step approach. The second step is if you already have a CO2 capturing facility where you have an absorber in place where CO2 is being captured, can we just stick in another reactor where we can chemically regenerate the amine and we can produce high purity calcium magnesium carbonates? So this is what we call as mode 2. Now let's look at what that gives us. So we just started doing this with calcium oxides and calcium silicates, and it turns out that with calcium oxides we can see close to 100% conversion at temperatures at about 50 degrees centigrade with 38% of the amine with mode 1. This is the mode where we have gas, liquid, and solid. With mode 2, where we just have liquid-solid contacting, we run out of CO2, which is one of the reasons why conversions are slightly low. Also with silicates, we see about 30% conversion. Silicates are harder to carbonate, but even that is pretty good. And all of this is at much lower temperatures of 50 degrees centigrade, not 150 degrees centigrade. Again, we looked at effective temperature, and we can do all of this at 50 degrees centigrade, so this is great. Problem is that we don't understand what is the cause of the polymorphism. So I just have maybe like 2 more minutes that I'll take up of your time. So we tend to see a lot of calcium carbonate phases form, but 3 different types, 2 metastable phases and 1 stable phase. So the 2 metastable phases are vaterite and aragonite, and the stable phase is calcite. Now we are trying to establish the surface science basis for why we expect to see this polymorphism occurring. And these are some of the characteristics of these materials, but where is it that we're going with this, right? So if you look at a lot of industrial decarbonization that needs to happen, a lot of industries, including power plants, steel plants, cement, and aluminum production, produce a lot of alkaline waste. We could actually offset some of their CO2 emissions, maybe not all of it, but some of it. right? We are able to do this successfully with asbestos-containing materials as well. We've been able to add some of these materials to construction materials and improve the strength of these materials. So slowly we're going into a world where we can have carbon embedded in the world around us. And what is it that we want to do in the context of negative emissions? So 10 years ago, people were like, yeah, we don't need negative emissions. But now we need approaches where we can produce a clean energy carrier like hydrogen while storing CO2 away at the same time. So this is one example where we can actually take biomass, react that in an alkaline environment to produce pure hydrogen, put away CO2. Also, we have the water-gas shift reaction where we can get pure hydrogen and start putting away the CO2 as well. Problem is that there's a lot of basic science challenges that we need to address, particularly when designing these multi-phase reaction environments. So we need to have a handle on the gas phase chemistry, on the aqueous phase chemistry, and characterize these solids as they're undergoing these transformations. So we are just starting a project where we are taking the water-gas shift reaction, very famous reaction, has been studied to death for the past 50 years. We can take CO, water vapor, convert that to CO2 and hydrogen using a catalytic route. Not much to innovate there, but what we can do two things. We can actually take the CO2, convert that into a carbonate, and in the process of doing that, we actually push the thermodynamics to the product side so we can start producing more hydrogen. And this is a multi-phase reaction where you have gas phase conversion, liquid phase conversion, and solid conversions all occurring in a single environment. So if we succeed in doing this, then effectively we have negative emissions all happening in a single reaction environment. So with that, in order to, again, address this scientific challenge, we are developing a lot of new tools and techniques. We are developing microreactor environments where we can in situ go in and watch what is happening. So instead of going into the lab and doing a reaction, characterizing the products and saying, oh, this is my conversion, we actually want to watch what is happening as these reactions are happening. So that way we can go in and we can understand where we need to intervene, where we need to stage a chemical intervention so we can get these reactions to operate the way we want them to. So with that, I know that I talked about a lot of different topics this afternoon, and I'm sorry if I exhausted you. But basically, I just wanted to give you a flavor of how we can use computational tools to understand fluid organization and transport behaviors, how we can use some emerging cross-scale characterization approaches to map some of the structural morphological changes, and what it is that we can do to engineer material and energy conversions, particularly for low carbon and negative emission pathways. So with that, I'd like to acknowledge some of our funding sources. Also, would not be possible without my excellent graduate students. They're all here at Cornell, and they're working away, I hope, in the lab right now. And a long list of collaborators at NIST as well as at national labs who help us develop some of these reaction environments and characterization tools. So with that, I'd be happy to take any questions at this point.
So in order to close out by 1:10, so we have some quick questions from audience. Especially from students, I think we still have a rule. They can, you can have a shorter report if you ask a question. Actually, I have a question. I have a question. So I read the carbonation for CO2 storage. I think the idea probably had been there for 12, 15 years. Right? What's the status? Like, have been like a demonstration project, or still we're talking about the lab, bench scale?
Thank you. That's actually an excellent question. So the question, those of you who haven't heard, is that what is actually the status of carbon mineralization? I mean, this idea was proposed 20 years ago, and what developments have been made? Like, has there actually been a demonstration? Turns out that they're in a place known as Iceland, very, very far away. Some of you may have been. There is a project where CO2 is actually being injected into a basalt reservoir, and they find much faster than expected carbon mineralization happening. So they expected from their transport models, it's 2 years. 2 years to mineralize
Okay.
the subsurface environment. What was traditionally thought to take maybe 10 to 20 years is now occurring at the timescales of 2 years. So that's one example. From an engineered standpoint, there's a lot of interest in, say, China in managing their alkaline and industrial waste. So they're not coming at it from the point of CO2, but they're coming at it from the point of what is it that we can do with all the steel slag that we have. So there is some interest in taking some of these carbon mineralization pathways. Challenge is that all of them involve a lot of pH, like high temperature, a lot of chemistry involved. We are trying to develop low temperature routes where we can cycle the chemicals through internally. So that is something that we hope to commercialize from our group.
Okay, thanks.